Welcome to Activity 2.2 from our book. And our learning target for today is we're going to analyze additional data involving the ocean floor and determining how this evidence fit into Wagner's theory of continental drift. So you've been exploring a lot of different evidence that Wagner used to support his theory. But one of the big hang-ups was he couldn't explain the mechanics of how the continents could move. So we're going to start shifting towards looking at the evidence that was eventually used to say, yep, indeed the continents did move, but we're going to learn it wasn't really the continents, that it was the plates. So first of all, Wagner continued seeking additional data after he first came up with his theory. Unfortunately, Wagner passed away in Greenland. He was there, remember, he was a meteorologist, and he was there setting up weather stations. And unfortunately, he got caught out in the weather, and he froze to death. Now, one of the things I do want you to look at is this is a simulation from zoomschool.com. And this is some of the stuff that Wagner didn't have access to, but we do. So just look at it for a little bit, and I'll let it go through a couple times. Here you see the ages and the years, and look, the blue is North America. So at one point in time, right here, Wisconsin would have been a tropical paradise. People might have gone to vacation to Wisconsin. You don't usually hear that in the middle of winter. Hey, let's go to Wisconsin. It's really warm this time of the year. Well, that was a long time ago. Nowadays, it's not quite so warm in the winter. But you can see how different pieces of the continents seem to fit together like a puzzle. Not all of North America was always connected to North America. Different pieces came from different places. So let me ask you this question. And I've already asked you this once in the unit. Where are the mountains located on the map? And you probably said a lot of them are located along the coast. It's where, and you are starting to figure out it's where the plates are interacting. But is this the only place that you see mountains? Well, that's the only place you see them on land. What if we were able to remove all the water? Are there other places on the earth where mountains are located? And that's what we're going to be exploring today. So we're going to look at images that match the pictures in the table. And you might say, what table is that? If you look on page 25, there are 3 pictures. And there's a notes section for the mountain ranges in the ocean, trenches on the ocean floor, and ages of the ocean floor. Just like your other activities, take as many notes as you can. You're going to be able to use this book in your test. So the more notes you have, the better it is. And I'll finish each one of the sections with some notes. If I'm going too fast, just pause the video and record your notes. So the first one is the mountain ranges in the ocean. And so for the longest time, scientists thought that if you went from North America to Europe, that the ocean would just keep going down, 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 or the ocean floor would keep going down, 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 and eventually it'd start coming up. They were really surprised to find a mountain range, not just a little mountain range, but a pretty big mountain range running right down the entire Atlantic Ocean. And with this map, you can see there's other mountain ranges under the oceans as well. And this really surprised scientists. Now, let me ask you this. Do you know what this ocean range running right down the middle of the Atlantic Ocean is called? Now, if you said the Mid-Atlantic Ridge, yeah, you're correct. Good job. Here's another close-up view of it. And I like this view. So we're going to be learning about the different types of plate boundaries. And overall, it's a divergent plate boundary. It's separating. And you can see this rift right here. But yet there's all kinds of these right here, these that run past each other. Those are actually transform faults. So even though it's a divergent plate boundary, there's lots of little transform faults located there. So these are some notes you can add to your notes pages on the mid-ocean ridges. A ridge is simply another term for a mountain range. Now the ocean ridges are volcanic mountains. The largest of the mid-ocean ridges is called the Mid-Atlantic Ridge. So how do you think this supported Wagner's theory? Well, scientists didn't know for the longest time what made things move. They didn't know there was plates. But now all of a sudden, with all this earthquake data, with this Mid-Atlantic Ridge, scientists starting to piece together that there are these plates and that there's boundaries And these boundaries are where there's interactions, and it's actually the plates that are moving. So the Mid-Atlantic Ridge was a piece of information that supported his theory of continental drift. Now, in your next box, it says trenches on the ocean floor. And here's a picture. The one I have is in color. The one you have is in black and white because the whole book is in black and white. But there's this huge trench right here. In fact, this isn't the same one, is it? Yeah, this is the same one. You can kind of see the word Cuba in your book. It's very faint because it's in black and white. But there's these trenches, and these aren't the only trenches that you find near Cuba. There's trenches all over the world, and they happen to be underneath the ocean. Well, what's happening is that you have two plates that are coming together. And if you have two plates, and one is an oceanic and one is a continental, or if you have two oceanic plates, one of them typically is more dense and will subduct underneath the other one, especially if it's an oceanic plate and a continental. Now, if two continental plates come together, one will eventually subduct, but it's more of a collision than anything else, and that's how you get to Himalayan mountains. So here we see one plate come together, and it's subducting underneath the other one because it's more dense. Now, as it's going underneath, it's not just sliding peacefully underneath. There's going to be lots of rubbing going on, lots of friction, and this is where you're going to have a lot of earthquakes happening, and see how it pulls it down with it. Now, eventually the rock gets to the point where some of it will start to melt, and that magma will come up and will form an island arc or volcanoes. So this is how you're going to get places like Japan. And as it's going down, again, it's starting to pull this side down as well. And this is where you get some pretty large trenches located. And over by Japan, you have another large trench. And as a result, you have Japan, the islands of Japan. So here are some notes you can add to your book. Trenches on the ocean floor. Oceanic plates and continental plate trench. They create a subduction zone, and the volcanoes are a result of this collision. So again, if we go back, you can see as it collides, you're going to have earthquakes, but as it's pulling it down, eventually some of the rock material that has a lower melting point is going to start to melt first. It works its way up. It forms volcanoes. That's why you have a lot of volcanoes on the island of Japan. But eventually they form islands. So they are creators in that sense. So the Andes Mountains are an example of this in South America. Now the Andes Mountains aren't an island arc like this, but here would be closer to land, and those islands or those volcanoes formed on land. But the Andes Mountains are very active today as a result of the plates moving underneath the South American plate. Now, if it's two oceanic plates, it creates deep trenches, volcanoes, and island arcs, such as the island of Japan. Now, the Mariana Trench is 35,994 feet below sea level. So that's pretty deep. So you can see that these huge trenches are created because of convergent plate boundaries, whether it's an oceanic and a continental, or an oceanic and an oceanic plate. The last column, or the last spot for notes in your book, is called the age of the ocean floor. And what you're looking at here, right here, is your Mid-Atlantic Ridge. And what scientists found out is that as you move away from the ridge on both sides, the age of the rocks get older. And this really puzzled scientists. Why is the age getting older as you move away from the Mid-Atlantic Ridge? Well, what they found out was that in the middle of the Atlantic Ocean, new seafloor is being created. So as the plates divide and move apart, new material from deep within the earth comes up and it takes its place. It's not like the earth is going to be moving apart and you're going to have a huge gap there and there's nothing. Magma's coming up, volcanic activity is happening, and new ocean floor is being created at that ridge. And then the plate is moving apart. More comes up and forms. The plate is moving apart. More comes up and forms. And this happens over many, many years. Geologically speaking, over millions of years. So what's happening is where you are right in the middle of this plate, new ocean floor is coming up. So it's going to be the youngest rock. And as you move away on both sides, it's going to be getting older and older and older. So it's not necessarily a perfect mirror image, but you can see where the oldest rock is, and on both sides, it's not quite a mirror image, but it's pretty close, where it's getting older and all of a sudden it's getting younger, and you see your different ages. So you see your oranges, your yellows, your greens on both sides. And the Mid-Atlantic Ridge is probably the best example of this, but you can see it in other areas as well. So, age of the ocean floor. The ocean floor rock is mainly basalt, and basalt is really a dense rock. And it was found to be much younger than the continental rock, which is granite. Approximately 200 million years on the ocean floor versus scientists or geologists think they have found rocks that's about 4 billion years on the continents. So the oceanic floor is much, much younger. And we're going to talk about why that is later when we talk about convection currents. Because ocean floor rocks, well, if we remember when we talked about trenches, ocean floor rock is more dense. So when two plates meet, it's the ocean floor that's going to subduct. And as a result, it's always being created, but it's also always being destroyed. Where continental rock can be destroyed, but it tends to be less dense and it tends to stay on top when there's a collision. So the age of the rock closest to the mid-ocean ridge is youngest, and the ocean floor rock is mostly volcanic in origin. Where if we look at continental rock, a lot of it's going to be, you're going to have some igneous, absolutely, but you're going to have a lot of sedimentary rock, at least towards the surface, as well as some metamorphic rock. So continental rock is volcanic, but it's metamorphic, more sedimentary in nature. So I think this is just another picture. So let's take a look here. Making sense. After looking at this new data, so we're on page 24. After looking at this new data, what did scientists conclude about how the continents appeared to be moving on the surface of the Earth? So go ahead, pause the video and answer this question. So now that you've had a chance to answer it, so what did scientists conclude about how the continents appear to be moving on the surface of the Earth? Well, after looking at all this evidence, the combination of the new data about the ocean floor, along with the older theory of continental drift, suggested that the ocean floor was moving in addition to the continents. Wagner didn't think this. Wagner talked about continents drifting. He never thought that the ocean floor was moving as well. So the continents used to be close together, forming one large supercontinent called Pangaea. But the formation of this new ocean floor led to the spreading of the ocean floor and the separation of the continental landmasses. So it made more sense that it's not just the continents that are plowing through the ocean floor. All the plates are moving, and they're moving in and around each other, as well as when they move towards each other, one will subduct underneath the other one. So all this new information definitely help support his theory. You might say, well, his theory was wrong. He just said the continents were moving. But that's a big step forward versus saying nothing's moving. So yeah, he wasn't quite there yet, but yet his continental drift theory still was the foundation of modern day plate tectonics. Now, here's your second question. Explain ocean floor spreading and how this process is related to the mid-ocean ridges. Well, ocean floor spreading occurs when new rock is formed at the mid-ocean ridge. This is a continuous process, and as new rock is formed here, it spreads from the center and moves away from the ridge. This explains why the ocean floor at the mid-ocean ridge is younger compared with the ocean floor moving away from the ridge. And we're going to learn that this is due to convection currents, where the warmer, less dense rock is rising to the surface. As it gets to the surface, it's moving to place, and as it cools off, it's going to fall back down to the Earth. And scientists believe that there's these huge convection cells inside the Earth. They don't always know exactly where they are and how they work, but this is one of the leading theories as to how the plates are moving. So as always, if you have questions, make sure you let me know. Here's some more background information. If you want to add something to your notes, you definitely can. We are going to be taking a quiz soon on lesson 2. And as always, make sure you study. Make sure you study your quizzes. We have lesson 3 to get through, then lesson 4, then we will be taking our first test. And these notes on page 25 will be really useful for the test. So thanks. Bye.